finally, you can start. And today we have speaker Kateryna Hlyniana with a talk about white noise process associated with Arratia flow. Please, Kateryna.
Okay, thank you. So I will show my recent results on this topic. So as usual, I will start from definition of the Arratia flow. I know that we repeated a lot of time here, but maybe some new participants needed. So I recall that the Arratia flow represents like it's random field that consists of Brownian particles that starts from each point of the real line, move independently, and after meeting two trajectories coalesce into one, and after that it continues to move like a standard Brownian motion. So here you can see precise definition of it, but maybe I will not stay here alone. So what is main object that we consider with Arratia flow? We can associate point process. So how we do this? So we know that for any positive time t, the image of real line is almost surely locally finite. So this means that for positive time in the interval u1, u2, you can find a finite number of points, or almost surely. So that's how we can define a point process n. So it just counts the number of points in interval u1, u2 that we have at moment t. So this point process is located on real line. So at each time t on real line, we have a random set of points. And this random point process is very interesting itself. And the work that we cited quite a lot, the work by Tribe and Zaboronsky, they considered this point process at time t, and what they did is that they find out the endpoint densities of this point process. So this means that you can find precise, like exact formula for probability that you can find a particle in dx1, dx2, and so on, dxn, and you can write the formula that is given by Pfaffian. But today, like I didn't write this precise formula here because I will not use it. But the question is like, what is the algebraic structure of endpoint density of such a process is quite interesting. But we can use these formulas to find out the parameters of limiting Gaussian distribution that we obtained in central limit theorem. So here I would like to say a little bit in more details. So if we consider one periodic function f, so I suppose it has mean 0 and finite second moment, I will say. Then we consider such integrals with respect to point process at fixed moments of time t1 and so on tm. So then you can imagine that we integrate over bigger and bigger interval n, and we use here the mixing property of the Arratia flow. So we proved the central limit theorem of this form that with standard normalization, such integrals will converge to a Gaussian vector. So now the question that we are interested in is their properties of this Gaussian process with respect to time. So as I said, we know the exact distribution of point processes at fixed time t, but we do not know how they depend on different times t1 and t2, for example. So here the question also by itself, like how we can find some probabilistic parameters of joint distribution of 2-point processes at different time t, but also be interested for this for limiting Gaussian process. So how we can find, so this is questions of investigation I write here. So for example, even to find a correlation function for Gaussian process that we obtain is not trivial. We get the formula, but the formula is quite huge and it's difficult to analyze it. And also another question, like how we can obtain like the Gaussian process at time t from maybe with some random mapping from a Gaussian process at time s. So this is the questions that we are interested in. But of course, like for now, we have more questions than answers, and I would like to show you what kind of approach we use to try to answer on this equations and what we get. So the first question about correlation function between for limiting Gaussian process, we have the following result. So for simplicity of notation, I will write such brackets for integral and denoting u star and u star upper index maximum of k points and u subscript star as minimum. And let us introduce a function q, which is given just by a density of the following probability. Here I denoted by phi the trajectory from Brownian net, that starts at point T1 at point A and at the point B. So we can consider here just two independent linear processes that coalesce after meeting. So this is a probability that two Brownian trajectories starting from points A and from points B met, and they are in subset delta. So this density can be obtained, and in this term we can find the covariance function for integral itself. So here, please remind, I recall that I now write the covariance not for limiting process, but I write covariances for integrals. So this is a first step that we can do in order to find an limiting covariance for limiting Gaussian process. And here you see quite difficult structure. We have here alternative sum with expected values of product of one-dimensional integral times k-dimensional integral. Here n power k, here we take so-called factorial powers of measure. So, well, yes, we can write this formula, and what I told before, Tripe and Zaboronsky, they found the n-point densities in terms of them. Well, technically you can write everything what is connected to moments of point process, moments of integrals with respect to point processes. So here you can write an answer using pfeffens of k order or in such summation. So yes, we got a formula, but this formula very difficult for analysis, even like for two integrals at time t and time s. So the how one could proceed for limiting Gaussian distribution, here you just need to write down the limit of the following product from 1 to from 0 to n, and just to divide by n. So this formula it can be obtained, and it's good that we have it. And one simple result that we can get from it now is to make such a conclusion. Maybe it's simple, but from just analyzing the summation like this, sum converge absolutely, and taken limit when t minus s tends to infinity, we can get, yes, that covariance between two integrals for large distance between moments of time tends to 0. Like it's quite natural, but we can get it. And the question like about speed of convergence, here a little bit more difficult, but is also of interest. Much more difficult to see what will happen, how covariance will converge to variance when t and minus s tends to 0. So this for now is open a question for us, and we can continue to analyze this sum. And the difficulty is just, yes, we can write the integrals in terms of functions of matrices, but to analyze this alternative sum is quite quite difficult. So we decided to try another approach that can be helpful for analyzing of limiting distribution of integrals, or just integrals of a function with respect to point process at different time itself. So for this, we can try to investigate an integral with respect to time t. So here the approach, okay, maybe we can find out that this is a martingale. Maybe we can write some like do Meyer decomposition, and then we can try to analyze how it behaves with respect to time t. So this approach I presented on my some previous talk, and here I just want to slightly recall what we can do in this approach and what questions arise here. So for simplicity, let us start from n fixed point, and we consider Brownian flows with coalescence that start from these points u1 and so on un. In this case, we simply can enumerate them, and then we can define moments of coalescence quite precise. We can just say that our trajectory with that starts from point uk will move until it meet one of trajectory with lower number u1 and so on uk. So this is represented here. And with this finite Brownian motion with coalescence, we can associate corresponding to a point process. I give here index n. And now corresponding integrals with respect to this measure n, nu, and we can write in such form of such summation. Sorry. So here we sum over those starting points which you can say is derive on to time t. So so y is, you can say, the time when a trajectory meet another, and die, so-called. So assuming that function f is smooth enough, we can apply it a formula for this product, and we will obtain the following representation. So here we will have a martingale part, which is represented as integral with respect to trajectory. So we have sum of integrals. We integrate a trajectory with respect to itself, and we integrate it up to time t, or the moment of coalescence. So here it's depend what trajectory we have. So here I draw them in yellow. So this means that we use all trajectory for integral. And then the part with which represent a part of with bounded variation. Here, so the second part we have just integral of a function along trajectory ds. And here the most interesting, we need to know the value of a function at the moment of coalescence. So we need to know what is this point in time and space. So we need to know coordinates of moment of coalescence and its position itself. So from this point of view, the idea that we use now, we want to investigate a point process that defined by moments and position of coalescence in Arratia flow. So this point process now is defined on the product time times space, and this point measure now it's just counts number of points of coalescence that occurs in time interval from S to T and located at subset delta. So now our idea is to try to find the properties of such point measure and sorry. And try to use this measure in order to find the shift from integral with respect to point process that we have at fixed time t, and this point measure that that detects moments and position of the coalescence. And so the question of investigation of this point measure is interesting by itself. And now I want to demonstrate on a simple example how we can use it to analyze limiting behavior and how we can get like what we say how we can get the limiting Gaussian process at time t from Gaussian process at time s by some random transformation. And to demonstrate it, we will consider very simple example. So here we will have all answers, and we will see that this approach it can be fruitful, but of course, in the case of Brownian motion with coalescence, it's much more difficult, and we need more analysis for it. So what simple model we consider? We consider at time 0, we consider a random set of starting points. So they are distributed accordingly to Poisson point process. So here at time t0, we have just standard Poisson point process with Lebesgue intensity measure. And then we will consider very simple dynamic with respect time. Time, we assume that point does not change its location, but it die after random time tau. And this random time of its life are independent random variables. So here the same, we can consider 2-point measures that fixed number of and positions of points at time t, and also we can consider a point process which is in R2 that fixed that determined by location of death, like at moment and place of death. So more detail, like we can, I here just describe how we can write more precisely the Poisson point process on R. We combine it from independent Poisson point processes on intervals n+1, and then we just merge them together. And how we kill all points, we kill them accordingly to sequence of independent, identically distributed, exponentially distributed random variables by the following formula. So we say that point will live until t less than this time of death. So in this form, like what I said, mu t represent just here on this picture represent the position, like if you just draw the vertical line, you will see what the location of survival points. And it's quite simple result that follows from standard Poisson point process theory. It will say that such point process with killing will be again a Poisson point process with intensity measure of such form. So we start from lambda Lebesgue measure, but with time the intensity measure tends to it's tends to zero, you can say. Okay, so as I said, we also will consider another point process which is located in time and space, that is exact location in of moment and of position of depth of a particle. So this point process will be also Poisson point process, but now on product, and we can write the intensity measure like lambda times here the distribution of one death point, which is so if we know that the point process Poisson point process and we know its intensity measure, we can easily find the all moments, and we can analyze also integrals with respect to this point process. So here I will repeat the all procedures that we did for a Brownian flow with coalescence for Arratia flow. So what we did for measurement that fixed the location of points at time t, we can consider such integrals. And here I want to note that we can rewrite this integral using their measure that counts also just states of death. So in this case, in our simple example is very easy because our points do not move, but in the Arratia flow, of course, we need to take into account that after death they will move. So if we know that we have deal with Poisson point process, then it's easy to calculate the expected value and second moment of integral. I write it here. So we see that moments finite, and moreover the integrals are independent, so we integrate over non-intersecting intervals, and due to independency our points do not move, they just die. So we will have independent random variables in with known first and second moment, and moreover we know the covariance between integrals for different point t and s. It's also not hard to see, and similarly we can define the integral with respect to point process, which is defined on a product time space. And here, of course, we will see what kind of assumptions on function g we should have in order to have here a finite integral. So there, now we can represent this like this sum. I just write what we have. So again, integrals with respect to this time, space, point process also will be, if we consider here independent non-intersected intervals, random variables will be independent. And we should have the following assumption on function g. So here we assume that g is one periodic for any fixed s, one periodic with respect to the first variable. And on the assumption that this integral is finite, we will have finite moments for integral jn, like for integral with respect to space, time, point process. And again, if we know moments, then we can easily get the central limit theorem for these integrals. So I write it here. So this is like very simple analog of central limit theorem, what we obtain like for Arratia flow, but for this example, like it's quite trivial, but the point that I want to show here that we can easily find the covariance function for limiting Gaussian process, and it has the following form. So this is just a simple calculation of covariance in multi-dimensional central limit theorem for independent identically distributed random variables. And most interesting, how we can connect that Gaussian process with Gaussian limit of integrals with respect to time, space, point process. So here, as I told, we have integrals with respect to point process that detect location and time of death of a point, and we will have following central limit theorem, and here we will have just a Gaussian random variable which is indexed by function g, and we simply can get its variance. Variance E sigma is calculated like by this formula. So now the question, yes, we can easily connect the Gaussian process from the first statement with this Gaussian element. So how we can do this? So we do this by using this connection between integral at fixed time t and integral with respect to time, space, point process. So I want to note once more that now it's very simple because our points don't move and we can do this. And now we can pass to the limit in this, like we normalize, and we can pass to the limit when n tends to infinity, and we can get the following connection between the integrals. Just for simplicity, I will define a generalized Gaussian element psi. I'm sorry, zeta dot, which will represent the limiting Gaussian variable for integrals for point process of location and time of death of particles. So the limiting Gaussian variable we can represent like in this form, like it's easier for us because we then can vary function g, and Gaussian element is independent on this g. And now using representation, how I say we can connect integral I and j. So integral with respect to moment, like for fixed time t and for time space variable. So here, like you see this function g that I integrated has index t. So this is a function like we just multiply function f, this function f, by indicator that s is greater than t. So as I write here, like for example, the integral one-dimensional with respect to time t, I rewrite in terms of integrals in space and time. And now applying central limit theorem to both sides, we get that the limiting Gaussian variable at time t plus h can be rewritten as limiting Gaussian variable at time t minus something. So I can write it in the following form, that with this notation, so just integrate formally Gaussian noise with respect to this second variable over st, and then we can represent, like we can get the additional part of Gaussian point at point t minus t plus h. We can see that we can get it from Gaussian variable at time t minus this additional part, which is defined by Gaussian noise that we obtain from time space point process. So here, this approach just show us that yes, we can try to connect the limiting point processes, limiting Gaussian processes at different time t plus h and t, and maybe we need to subtract something that is defined by point process on that's detect location and time of coalescence. So this is a simple example that illustrate for us what we can try to obtain and what we hope to get for Arratia flow. Of course, for Arratia flow, everything much more difficult. And for now, like, what is next step that we want to obtain? We want to consider a Brownian flow with coalescence that starts from some finite number of points. But we decided to choose them also randomly, so like to make the previous example more difficult. Now we start from Poisson point process, but I'm sorry. Oh. Yes, now we will start from Poisson point process, and we will consider the moments and like at when and where the two trajectory coalesce. So, and also we will consider like because we want to get some for now we want to get stationarity with respect to time and space. So here we decided to consider their Poisson point process that starts from R2, and we consider these points as starting points for Brownian motion with coalescence. So again, I didn't write here precise how we define the Poisson point process, and so we can choose enumeration for points, and then we can decide in which order we can will coalesce, we will merge independent Brownian motions. So here just write that we want to build a model of Brownian motions with coalescence that starts from Poisson point measure. So here on this picture, blue dots represent a point measure, just Poisson point measure of starting points. So it's random, but like we can assume that because of independence of Brownian motion, so it's random, but independent of coalescent Brownian flow. And from these blue points, we start independent Brownian motions that coalesce, and we can define here the point process that fix the location and time of coalescence. So they are represented by red points. And similarly, with this previous example, we can consider a point process that at time t, just it detect the location of particles. So here now for this generalization of the previous example, so now we start from Poisson point process, but now we move, and now we have another point process of allocation and time of you can say death. I say that when one point meet another, it die at that moment. So now the question of interest to find out the properties of this point measure that detects this moments of death. And we have some properties of this point process which we obtain in R2. So it will be stationary. So this means that if we shift subsets delta, the the distribution law will not all change. You can shift them on the same page. And also, we will have stationarity with respect to time and with respect to shift over space for measure mu t that we here for fixed time t, we just detect location of points. And because of stationarity, we will have the finite first moments because now they just proportional to Lebesgue measure, respectively on R2 or on real line. And because, but now is a more tricky question that this red point process, we cannot expect that it will be a Poisson point process because we cannot expect that this red dots will be independent on different on non-intersection subsets. Why is it so? Like, because if I want to count here on not intersected subsets, I want to find the number of red points. But you see, one Brownian trajectory can affect the location of a point in one subset, and then in another, even these subsets are not intersecting. So in general, we cannot expect that we will have Poisson point process. And now, like, the interesting question, what kind of correlation structure we will have for this point process. But for now, what we can easily get that from finite moments of Poisson point process, and that we just, you can say, we shifted on independent Brownian on independent Gaussian variables. Then we will have finite second moments, and using alpha mixing for Brownian flow with lesson, we can get the central limit theorem for integrals with respect to measure mu t that fix just location and point at time t. So this we can get, and now the next question will be how we can connect the limiting behavior here, the limiting Gaussian process that we get here for Gaussian for limiting Gaussian process that we can get again, as we saw in the example of Poisson points that don't move but just die. We have this connection. So now next step is obtain this kind of connection here. But for now, this is what we are doing, and this, I hope that this will be in the next talk. I will try to finish this work, and we will represent it. So here I just wanted to show the idea that we trying to use, and some examples may be simple, but we hope they can show us what we can expect and what tools we can use in order to obtain result for Arratia flow. So for now, that's all what I have, and thank you for your attention.
Okay, thank you very much. Maybe somebody have questions or comments, please. Yes, it is. It seems that we need some formulas again of the sort, like in one-dimensional case you showed us at one of the first slides, where we have actually a relation between correlation functions for Arratia flow in different moments of the time. Here we have the same structure, but only on the plane. I think that this Poissonian prose on the plane of course is Pfaffian prose. Yeah. No, it is determinantical prose. I think. Yeah, but after this, we just use again the random mapping with which is organized by these trajectories with coalescence.
Yes.
So I think that it can be calculated more or less in the same style as we did in one-dimensional case.
Yes.
So the hope is that we will finish this work soon, and we will get a lot of Gaussian noises related to point process. Okay. Okay. If there are no any other questions or comments, then I think that I know that the next speaker is Gani Hadjayev, Nasir Nabievich, yes?
Yeah, yes, yes.
Okay, good. So we
Okay,
will wait for your talk next week.
okay,
And
thank you.
for today, that's all. Thanks everybody and see you next week. Bye.
Okay, bye. Bye.
Спасибо, Катя, выздоравливай.
Спасибо.
Всего хорошего.